Okay, if you'd like to, we'll continue on and start talking about conventional fluoroscopy. This is probably going to be the longest section I want to spend time on and kind of explain to you how the fluoroscope works, and then also digital fluoroscopy and the difference between the two. Again, this is one of the old GE fluoroscopes. So this is the fluoroscope here, X-ray tubes behind, and this is connected to it and rotated up and down. This is the new digital fluoroscopy units that they're using in most hospitals now today. So we've come a long way, baby, right, in the last 50 years. Okay, so some of you are familiar with the conventional fluoroscopic X-ray or conventional fluoroscopic room. A lot of times in a department we call it an R&F room. It does radiographic exposure and fluoroscopic exposure, so it has a separate X-ray tube. But in a fluoroscopic room, if it's a dedicated unit or if you have a stationary fluoroscopic room, the X-ray tube is actually located underneath the table base. The table base is lead lined, therefore there's no scattered radiation to the operator other than the radiation coming off of the patient. So we're not worried about X-ray coming out of the X-ray tube, X-ray hitting the table base, and then bouncing out, that sort of thing. So this is really a nice setup if you're in a stationary unit. Most of you, however, work with mobile units, right? C-arms. With a C-arm, the disadvantage is there's no table to protect you from the scattered radiation and from what we call the leakage radiation that's coming out of the X-ray tube. So stationary units do have an advantage in that the X-ray tube below the patient it's protected in the table base. So this produces the X-ray just like a normal X-ray machine. The only difference is during fluoroscopy, the X-ray is continuously produced. If I take a chest X-ray of somebody, I'm exposing them for about a millisecond, about 1,000th of a second. When you do fluoroscopy, we typically use very low MA, 1 to 5 MA, but our time factor is variable, right? The time factor is usually in seconds or minutes. Okay? So that makes a huge difference when you're using a millisecond for a chest X-ray, giving a person 10 MR, and you're using minutes in fluoroscopy. What's the difference in dose? Well, for a chest X-ray, like I said, 10 MR for a chest X-ray, typically in fluoroscopy, about 4,000 MR per minute. 4,000 MR or 4 R per minute for a typical fluoroscope. Now with digital fluoroscopy and pulsed imaging, we'll talk about that later, it's less now, about 2. But with the conventional fluoroscopic units, average is about 4. Now can that go up? Absolutely. Bigger patient, higher mass, more exposure. Smaller patient, less mass. But that will give you an average. Okay, so how does this thing work? Well, we have X-ray that's located below the tabletop. Above the X-ray, this is our receptor. It's kind of like what you would use for your film or your digital plate. The receptor is the image intensifier. And what it does, compared to the old plate that you had over the old fluoroscope where we had it over the patient, the old fluoroscope was made out of calcium tungstate. The X-ray went through the patient. The fluoroscope fluoresced, gave off light, and then they looked directly at that fluorescent screen. That was done in complete darkness, right? They had turned all the lights off. Why? The light that was emitted from the fluoroscope was not very bright. It was very dim. You had to use your night vision actually to see it, which is, our night vision is not as good as our daylight vision. About 2200 for night vision as compared to 2020 for daylight vision. So radiologists were in the rooms with the patients for a longer period of time. The exams took longer. They got higher exposure levels. In 1950, they came up with the image intensifier. DuPont invented it. And the idea was to take the light that was emitted by the fluoroscope and somehow to intensify it, to make it brighter so that the patients would get less radiation, so that the radiologist would be exposed less time, and the image would be more visible to our daylight vision so that we could see it better. If your visual acuity is better with your daylight vision, it only makes sense that if you brighten the image, you're going to be able to see it better. So the image intensifier was a means of brightening the image, of making it bigger, and also being able to view it other than looking directly at it on a monitor. Okay, so it had to kind of be not digitized, but it had to be changed from light to a video signal to get to the television monitor. Now there was an old form of viewing on image intensifiers, and some of you may have seen it. It was called mirror optics. Did you use mirror optics? where you looked actually at a mirror on the image intensifier rather than a television monitor. So there was a system of mirrors attached to the image intensifier, and kind of like a projector that has the mirror on it, you'd look directly at a 4x4 mirror at the output phosphor of the image intensifier to see the image. Okay. The disadvantage is it was a very small image, and only one person can look at it at a time. When we came up with the television monitor, which is a CRT cathode ray tube, we're not using those anymore either, are we? So those are pretty much gone. But this whole system is being replaced by the digital system. So the image intensifier was a means of brightening the image, and it did that with a gas evacuated vacuum tube. And the image intensifier tube is covered with cesium iodide at the input phosphor. So the X-ray strikes the input phosphor, it's converted to light. Then it strikes a photocathode. Cathode means negative, right? The light photons are converted to electrons, and then they apply voltage, 25,000 volts across the tube, so the electrons are accelerated at about half the speed of light from the input phosphor to the output phosphor, where they're converted back to light again. Okay? Now the output phosphor, the input phosphor can vary in size. Most typically the input phosphor is about 9 inches in diameter. But the output phosphor, regardless of the size of your input phosphor, is always 1 inch in diameter. So basically, you're taking 9 inches of light, and you're going to reduce it down to 1 inch of light. So the light's going to be brighter, right? It's more condensed. It's actually 81 times brighter if you have a 9-inch input phosphor and you square that over a 1-inch output phosphor and you square that. The brightness of the light is 81 times as bright in any given area on the output phosphor. Okay? So that's one way that we brightened the image. The other way that we brightened the image was by increasing the energy of the X-ray, if that's possible. X-ray is electronically neutral, so it already is traveling at the speed of light, right? But after it passes through a patient, it really does lose energy. The wavelengths become longer and softer. So when they hit the input phosphor, they don't produce a lot of light. By converting the X-rays to light and then the light to electrons, we can accelerate the electrons, increase their kinetic energy, so that when they strike the output phosphor, they give off more light than those X-rays that struck the input phosphor. And that's called flux gain, or electronic intensification. So it's these two means, by minifying the image from the input phosphor to the output phosphor, and by accelerating the electrons across this vacuum tube, that we're able to brighten the image at the output phosphor, or intensify the brightness of the image. So it's done through minification gain, and flux gain gives us our overall brightness gain. A typical image intensifier will brighten your image anywhere from 10 to 30,000 times brighter than the old fluoroscope. Okay? Now, once we get the image bright enough, how big is it at the output phosphor? 1 inch in diameter. So now we have to figure out a way to magnify it so we can see it. That was typically done with a television camera tube. So they put a television camera right at the exit of the image intensifier, right here. And what the television camera tube does in essence is it converts the light image to a video signal. Now the way that it does that, I mean, if you want to take a 10-hour fluoroscopy course and take the California exam, Nat can tell you he learned all about how to convert a light image to a video signal, but that's not necessary for this. Just knowing that the television camera tube, which is a glass vacuum tube with a cathode and an anode, so it's subject to burnout, and this, when your fluoroscope goes out, it's usually the camera tube that burns out because it's got a smaller filament in it. The television camera tube basically converts the light image to a video signal. That video signal is carried through closed circuits to the television monitor, where it's converted back into a visible light image again. Okay? Now there's 3 tubes that we're dealing with here. We have the X-ray tube that operates at, kVp, thousands of volts, usually 50 to 110,000 volts. It creates X-rays in a vacuum tube. Then we have the II tube, the image intensifier tube. That's also a vacuum tube that converts X-ray to light to electrons back to light again. Okay, so basically it's converting X-rays to light. That operates on 25,000 volts of current. And then we have the television pickup tube, or the television camera tube, and that operates on about 250 volts. That converts the light coming off of the output phosphor to a video signal which is carried to the television monitor. The television monitor also has a cathode ray tube. It has a filament and a cathode and an anode, which is the target, the actual screen, and it projects electrons to the screen, which is a phosphor which gives off light. So basically you're converting the image, the radiographic image, into a monitor image that you can visualize on the screen with the cathode ray tube. Okay, so what's the difference between conventional fluoroscopy and digital fluoroscopy? Well, the biggest difference in, the first conversion, just like we went from film screen to CR to cassettes, right? The first generation, the main difference between the two systems is the camera right here. Instead of the television camera, we have the CCD, which we said was what? Charged couple device. The charged couple device. So instead of a camera with a filament and an anode in it, we've got a charged couple device, which is going to take the light off of the output phosphor, and in the silicone is going to convert that light to an electrical signal, and that electrical signal then will be captured by these things called thin film transistors, which are basically capacitors. They'll capture the charge and then send that charge to the television monitor, which is like a computer screen, right? These flat panel monitors. So the two differences between this is one, the camera device, which is a charged couple device, which never wears out, lasts forever and give you much better, sharper images, and the television camera tube that's located here. And the second difference is the flat screen monitors that it operates with, as opposed to your old-fashioned TV monitors or the cathode ray tubes. Now, the resolution of a cathode ray tube is about 525 lines, vertical line rate. The resolution of the flat panel monitors is about 1023, double the resolution. Radiologists read at even higher resolution, usually 2048 monitors or 47. The numbers are always odd, but double the resolution of the monitors that we use in our rooms. So more pixels, more data, more information, more resolution. So that's the main difference. And then, of course, you have the analog to digital converter that takes the information and converts it to a digital image from an analog light image to a digital image, and then the computer that you process it with and store it. Okay, so digital fluoroscopy, the advantages that we have over the old-fashioned is the speed of acquisition time and the post-processing to enhance contrast. That's a big deal in digital fluoroscopy. So spatial resolution is, again, it's limited by your pixel size. With digital fluoroscopy, the pixel size is normally 1024 by 1024, the image matrix size, although the radiologists, like I said, they read at a higher rate, 2048. And again, the spatial resolution will be determined by the number of pixels that you have on your monitor. So digital fluoroscopy equipment, it looks a lot and operates just like the old-fashioned type, with the exception that there's more computers and you're going to have a higher contrast resolution with the digital. So the computers attached to these, you can do all sorts of things with the computers. You can put the patient's demographics in, you can do measurements with the computers, you can do post-processing with the computers. They've got all of the bells and whistles that your computers at home have as well. Now, most of the units that we have today, there's two ways that these can be set up. You can have the X-ray tube on top and the image intensifier on the bottom, or just the opposite, the image intensifier on top and the X-ray tube on the bottom. Okay? The tube current for digital pulsating current, what we call the, usually operates at hundreds of MA instead of your 5 MA. So that automatically is going to give you more data, more information, or a higher resolution of the image. Why can it operate on such higher MA as compared to the conventional units? It has to do with the electrical supply to the machine. Okay, the new digitals operate on what they call pulse radiography or pulse current, whereas the old ones ran on 3-phase 6 pulse. We had 3 phases of electricity and 6 pulses per 60th of a second. So a total of 360 pulses per second with the conventional old machines. The problem with those type of machines were heat units. So we had to use very low MA because the X-ray production was so high being produced. So two problems, you could burn the patient or you can burn up your generator. With normal X-ray, we usually use 100 MA or higher with a static X-ray. With a fluoroscopic image, we're using continuous exposure at very low MA and high KVP. But the X-ray machine is pulsating consistently, 360 times per second with 3-phase 6-pulse unit. The newer units, we're going to use a higher MA but less pulses, which you'll see in a second. Okay, so pulse progressive fluoroscopy is the latest, greatest thing. Everybody loves it because in 1 second, or 100 milliseconds, right, is 1 second, you're only exposing 1/10 of that time, whereas in conventional fluoroscopy, you're exposing continuously during the entire second, giving a patient in 1 second 360 pulses of X-ray with very low MA, very low current. In this type of fluoroscopy, you're using, I keep hitting the wrong button here, you're only pulsating, this is called duty time, we're only pulsating 1/10 of a second. So out of every 1,000 milliseconds, the exposure is 100 milliseconds of exposure to the patient with higher current. Okay, higher current means more X-ray photons, more data, but 1/10 of the exposure to the patient. So you're lowering your exposure to the patient by this pulsating current. Some people call it, you also get with this type of imaging, you get something called last image hold, where you can see your image on the monitor and it will stay there until you take another, until you energize the beam again and pulse again, and then you'll produce another image. So you can have greater variation of exposure. The patient dose reduction is much higher. I'll show you some numbers in a second with this pulse progressive fluoroscopy as opposed to the old-fashioned continuous fluoroscope. So the generators in the X-ray tubes are different the way that they're set up for pulse fluoroscopy. So the actual time of exposure is called duty time, okay, and it's usually 100 milliseconds. So about 10% of the exposure that you would normally get. Now the capturing device on these digital systems, like I said, is called a charge coupled device. This is first generation. When you get to direct exposure, they're going to be a little bit different. But the first generation machines, and this is what most of us have in our departments now, unless you're working in a cath lab or interventional radiography lab, but they're still using the charge coupled devices instead of the television camera to capture the light coming out of the image intensifying tube. Now the difference between the first generation and the second generation, first generation with the charge coupled device, second generation they eliminate the image intensifying tube. That's gone. So instead of having, think about the cassette and then going to the direct exposure on the table, they're going to go from the image intensifying tube to what's called a flat panel image intensifier that exposes the cesium iodide, which is captured by the selenium, and directly to the flat panel detector, which sends the image to the computer. So the whole image intensifying tube is gone on the new flat panel detectors. So a charge coupled device instead of a television camera. The pixel array for these charge coupled devices is 2048 by 2048. This is at the output phosphor of the image intensifying tube, and it's going to convert your light to a digital image for you. Doesn't break down. That's the great part about it. So basically, here's the light coming from your output phosphor, which is on the image intensifier, goes through the silicon and is converted to electrons, kind of like your latent image. Those electrons go to the thin film transistors, which create the current, kind of like a capacitor, and then that is sent to the computer to give you your image. Okay, so where is this charge coupled device? Well, it's the same place the television camera used to be. It's right at the end of the output phosphor in the first generation digital machines. Remember, the first generation digital machines still have the what? The image intensifier. Newer generation machines, the image intensifier is now gone. And spatial resolution for these is pretty good, 10 line pairs per millimeter, okay? Because you're using higher MA to produce your images. Okay, we also have something called automatic brightness stabilizer. In the old image intensifiers, this was called automatic brightness control. We called it ABC. Now it's ABS, automatic brightness stabilizer. And what this is, it's a photocell that measures the amount of light coming out of the output phosphor and adjusts the tube current for the amount of light, to keep the amount of light consistent. So if you're x-raying a patient that's really thick, less light will come out. It will automatically put more radiation through the patient. A patient that's thinner, the amount of light coming out would be greater. It will decrease the exposure. So it automatically adjusts the tube current to the thickness and the amount of light being produced by the image intensifier. What advantage is that? You always have a consistent image on your monitor that you're seeing, regardless of the thickness or thinness. So let's say you're doing a barium swallow on a patient, and you start off at the mouth, which is thinner, and then you run your image intensifier down to their stomach. Well, from the time you go to their mouth or their stomach, the image should remain constant throughout that thickness variation of the patient. Okay, again, with a charge-coupled device, you have this huge latitude of grayscale that you can use as compared to the old-fashioned film system. So you have greater sensitivity to the light, which means a lower dose. The charge-coupled device is actually able to detect more light photons, and we call this the detective quantum efficiency, DQE. And so you have less noise. Noise means we have a blotchy image. It's actually able to capture more of the light photons being produced from the output phosphor, thereby making it a faster system. And a higher signal-to-noise ratio. Signal means the light that's being produced, and noise is kind of scattered radiation that's produced in the background. We like to eliminate the noise and enhance the signal. And this is much better done with digital as compared to the conventional. So this results in, when you have a higher signal-to-noise ratio, it results in better contrast, less graying, kind of like scattered radiation. So the advantages of using a charge-coupled device versus the old-fashioned digital fluoroscopic unit is high spatial resolution, a higher signal-to-noise ratio, high quantum efficiency, that's how much light the CCD can capture as compared to the older system. There's no warm-up required. How many of you know what image lag is? Kind of a streaking that you see if you move a fluoro tower too fast. There's no lag with these systems. No spatial distortion. We used to produce a spatial distortion because the shape of the input and output phosphor give you kind of a blooming effect towards the edges of your image, known as vignetting. Okay? Really no maintenance because we're not working with tubes anymore. This is all semiconductors. Semiconductors don't wear out. They're great. And unlimited life. It's unaffected by magnetic fields. Okay? As opposed to the older systems that had the focusing lenses. A linear response rather than the H&D curve, and lower patient doses as a result. I'm not trying to sell digital, I'm just telling you why they converted over to it, okay? I have no vested interest in this. Okay, so digital fluoroscopy, if you were to put it in your department or something, you would have a wider range of contrast. You're going to have a lower dose, better resolution, because of this grayscale that we can pull out in post-processing. It's great for subtraction. For those people that do angiography and things, the subtraction capabilities of digital are much, much higher than the old conventional methods. Now the latest craze now, and the third generation or actually probably second generation of fluoroscopy is called the flat panel image receptor, where the image intensifying tube has been replaced by cesium iodide charge coupled device. So the whole image intensifier with the higher mass that we can use now, we don't have to multiply and accelerate the electrons. We can capture them with the cesium iodide producing the light, and then the silicone producing the electrons and converting the image to digital. Now the advantage of this is they're smaller and lighter. This is the X-ray tube under the table with a spacer. This is the flat panel device here, so you can see it's smaller to use, okay? Easier to manipulate. The surface is square instead of round, okay? So it matches the monitors, so you get less distortion of your image because of the footprint. There's no veiling glare, which is that vignetting that I was talking about before, and no pincushion distortion, which is a curved surface going to a flatter surface, which gives you the flaring along the edges. So these tend to have better resolution, are faster systems, and overall better. Okay, the other thing that's changed with the system now is that we're no longer using the cathode ray tubes as our monitors. They're using the flat panel display monitors. So most of you, how many of you have flat panel display monitors on your computers now as opposed to the big TV monitors? How many of you have flat panel television monitors? Okay. There's a little bit more outlay initially as far as the cost goes, but overall, like I said, the footprint of these images fit better on these. They're easier to view and manipulate. All radiologists now that are reading digital images have these monitors in their office. The old view boxes, the multi-loaded view boxes that we had with the hundreds of panels, those have pretty much gone by the wayside. So we used to use these old television monitors, 525 lines and 30 frames per second. Well, the frame rate hasn't changed. It still takes 33 milliseconds to produce an image, but we don't scan the same way, and there's no interlace mode production. So what happened in the old CRTs is you had an electron gun in the television monitor that would scan the target every other line, 262.5 lines in a 60th of a second. Then it would go back the second time and scan again to pick up all 525 lines. So it scanned one time to get half the image, a second time to get the other half of the images. So it took 2/60th of a second to get one image. So that's 2/60th of a second is 1/30th of a second. You would produce 30 frames per second with this horizontal interlace scanning. Okay? That's the way the old systems work. The new systems don't work that way anymore. They scan from top to bottom all lines at once. It takes 33 milliseconds to scan, but there's no interlace in that, and it has a higher signal-to-noise ratio. So no interlace scanning like this old system was, where we scan from side to side and front to back, and a lower noise ratio. So most of the places that you work now, you're going to see these flat panel monitors that work in this progressive mode with the pulsating. It's called a progressive mode scan, and they scan from the top of the monitor straight down to the bottom in a homogeneous beam. There's no interlacing fields, and this produces a sharper image without the flicker that you see in the old monitors. The interlace scanning was supposed to eliminate the flicker, but occasionally you would see it, and we called it noise, basically. And these have a much higher signal-to-noise ratio. And in fact, the old monitors don't work well with the new systems because of the amount of information. Analog devices are noisy. They've got that filament in them that constantly gives off current whether the image is being produced or not. So the heated filament causes background electronic noise, and which degrades your image. So this is just showing you the intensity of X-ray here. This is the signal-to-noise ratio for a CRT, and this is the signal-to-noise ratio for the video. So signal-to-noise ratio just has to do with filters and how much of the image, the real image, which is the signal, can be picked up and how much of the noise can be eliminated. So the greater the distance between those two, here and here, the easier it is to detect, whereas this is almost the same all the way around. So the noise is more difficult to detect here. So you're going to have more noise with this system than you will with this system. This image is 5 times better with a signal-to-noise ratio of 1,000 to 1. Okay, so 1,000 to 1 provides 5 times more useful information because you're not getting, think of noise as scattered radiation in a way to think of it. More compatible with the new computer systems that we're using, and higher resolution as a result. So pretty much everybody's gone with the new flat panel to replace the CRTs. Now that's, again, a lot of information in a short period of time. Questions about conventional fluoroscopy and how the image intensifier works? Digital fluoroscopy, which probably most of you are using now with your C-arms up in the OR. If they've got flat panels on them, you're probably working with digital. Either you're all overwhelmed or bored out of your mind, or yes.
I'm using a CR1 band as a user for various walls. Now you said KV goes through.
KVP.
KVP. Goes through the patient.
Right. The higher the KVP, the more penetrating.
What's the best way to get a continuous image, a uniform image from like the head to the stomach?
Well, your machine should be doing that for you. All of the units that we have now, if they're the older conventional units, they have automatic brightness control. So the amount of radiation going through the patient is going to be determined by your photocell at the output phosphor. Sometimes if you're over the barium itself, that can cause a problem because if you don't have any soft tissue around it, if the whole image intensifier is filled with barium, what happens is the X-ray can't get through, and so it continues to increase the dose to the patient because it's counting the X-ray photons that are coming through the patient. They're all being absorbed. So, you know, centering your part, limiting the amount of barium that you're putting on the screen at any one given time, and then the automatic brightness control should adjust the amount of radiation going through the patient for thicker and thinner body parts automatically.
Well, that's
I don't think our machines have that automatic. We have to, turn it up. One thing we can probably do is just collimate it.
Yep.
Just focus it down on the esophagus. We manually just turn it up until it gets to about 90 to 95 kVp, and then the machine turns off. Yeah. Sometimes just can't do it because the patient's just too much mass.
Yeah, sometimes if you're working with a very low MA system too, and you've got a thick patient, they're absorbing the radiation. So your only option is to increase your KVP to try to get more of the photons, but that's going to affect your contrast. You're going to get a grayer shade of contrast.